So, good morning, everyone. This is Dr. Perumal from Department of Chemical Engineering, Erode Sengundra Engineering College. Today, we will throw some lights on root locus method. In control theory and stability theory, root locus method is a graphical method to explain how the roots of the characteristic equation varies with variation in the process parameters, mostly the controller gain. If we vary the controller gain, how the roots will vary? This will be graphically represented by root locus method. So consider a simple feedback control system shown in the figure. The transfer function for the system shown in the figure is G1, G2 and H. G2 is the transfer function for process and G1 is the transfer function for controller. H is the transfer function for measuring element. So the transient response C equal to G1 G2 divided by 1 plus G into R plus G2 divided by 1 plus G into U. Here G equal to G1 G2 H. The characteristic equation for this control loop is given by 1 plus G equal to 0. The roots of the characteristic equation determines the form of response to any particular forcing function, that is change in load or change in set point. So the definition for root locus method. The root locus method is a graphical procedure for finding the roots of 1 plus G equal to 0 as one of the parameters of G varies continuously. The parameter that will be varied is the gain or sensitivity of the controller. In control theory and stability theory, root locus analysis is a graphical method for examining how the roots of a system change with variation of a change in gain or a feedback system. The root locus plots the poles of the closed loop transfer function in the complex plane as a function of gain parameter. So now let us discuss what is poles and what is zeros. The roots of the numerator of the transfer function is called as zeros and the roots of the denominator of the transfer function is called as poles. So the individual transfer function of each component of the control system shown in the figure is given as G1 equal to Kc, G2 equal to 1 divided by tau 1 s into tau 2 s plus 1, tau 1 s plus 1 into tau 2 s plus 1 and H equal to 1 divided by tau 3 s plus 1. The open loop transfer function is G equal to Kc divided by tau 1 s plus 1, tau 2 s plus 1 and tau 3 s plus 1. So this may be written in alternate form G of s equal to K divided by s minus P1, s minus P2 and s minus P3, where P1, P2, P3 are the poles of the characteristic equation. So the poles means it is the denominator of the transfer function. If s equal to P1, the denominator of the transfer function equation will become 0, hence G of s approaches infinity. Therefore P1 equal to 1 by tau 1 is the characteristic equation of the open loop transfer function is 1 plus K divided by s minus P1, s minus P2, s minus P3 equal to 0. This equation may be written as s minus P1 into s minus P2 into s minus P3 plus K equal to 0. Let the poles of the transfer function is minus 1, minus 2, minus 3. So substitute the value for P, s plus 1, s plus 2, s plus 3 plus K equal to 0, where K equal to 6 Kc. So expanding the product of this equation, s power 3 plus 6s squared plus 11s plus K plus 6 equal to 0. If you assume a value for k and substitute the k in this equation, you will get s cube plus 6s squared plus 11s plus 32.5 equal to 0. So solving this equation, we will get the roots r1 equal to 5.10 or r2 equal to minus 0.45 minus j 2.5 and r3 equal to minus 0.45 plus j 2.5. So 3 roots and 3 poles we get. Then to substitute the value for k and you tabulate the roots r1, r2 and r3. So the plot of roots r1, r2, 3 is a complex S-plane. This continuously changes with the variation in the controller gain k. So this is called as root locus plot. So it is a schematic diagram of a root locus method. There are 3 loci or branches corresponding to the 3 roots and they are emerge or begin with k equal to 0. At the poles of the open loop transfer function minus 1, minus 2, minus 3. Here we have 3 poles, minus 1 and minus 2, minus 3. So these poles are plotted in the root locus graph. It starts with k equal to 0 and the 3 branches we obtain. The direction of increasing k, that is controller gain, is indicated on the diagram by an arrow. Also the values of k are marked on each locus. So let me sum up. The root locus diagram has a distinct advantage of giving at a glance the character of the response as the gain of the controller is continuously changed. The diagram reveals 2 critical values of k. One is k2, one is at k2 where 2 of the roots become equal and the other is at k3 where 2 of the roots are pure imaginary. It should be clear that the nature of the response Ct will be depend only on the roots r1, r2 and r3. If the roots are real, which occurs k less than 0.39 in figure, the response will non-oscillatory. If 2 of the roots are complex and we have negative real parts, k2 less than k3, the response will include damped sinusoidal terms which will produce an oscillatory response. If we adjust the controller gain such that k is greater than k3, 2 of the roots are complex and have positive real parts and the response is growing sinusoidally. So rules for construction of root locus. Step 1. Locate open loop poles and zeros in the S-plane. Find the number of root locus branches. Starts at open loop poles and ends at open loop zeros. N equal to P if P is greater than or equal to 0. So N equal to Z if P is less than 0. Identify and draw the real axis root locus branches. If the angle of the open loop transfer function at a point is an odd multiple of 180 degree, then the point is on the root locus. If odd number of the open loop poles and zeros exist to the left side of a point on the real axis, then the point is on the root locus branch. Therefore, the branch of points that satisfies this condition is real axis of the root locus branch. Then fourth step, find the centroid and the angle of asymptotes. If P equal to 0, then all the root locus branches start at the hit point open poles and end at finite open loop zeros. If P is greater than 0, then Z number of root locus branches start at finite open loop poles and end at finite open loop zeros, and P minus 0 number of root locus branches start at a finite open loop poles and end at infinite open loop zeros. If P is less than 0, then P number of root locus branches start at the finite open loop poles and end at finite open loop zeros, and Z minus P number of root locus branches start at the infinite open loop poles and end at finite open loop zeros. So sum of the root locus branches approaches infinity when P is greater than or equal to, P is equal to 0. So we can calculate the centroid alpha by using the formula sum of real finite open loop points minus sum of the real part of finite open loop zeros divided by p minus 0, p minus z. The formula for angle of asymptote theta is theta equal to 2q plus 1 into 180 degree divided by p minus z, where q equal to 0, 1, 2, 3, p minus z minus 1. Then fifth step, find the intersection points of the root locus branches with an imaginary axis. We can calculate the point at which the root locus branch intersects the imaginary axis and the value of k at that point using the Routh array. If all elements of any row of Routh array are 0, then the root locus branch intersects the imaginary axis and vice versa. Identify the row in such a way that if we make the first element as 0, then the elements of the entire row are 0. Find the value of k for this combination. Substitute this k value in the auxiliary equation. We will get the intersection point of the root locus branch with an imaginary axis. Then find a breakaway and break in points. If there exists a real axis root locus branch between two open loop poles, then there will be a breakaway point in between these two open loop poles. If there exists a real axis root locus branch between two open loop zeros, then there will be a break in point in between these two open loop zeros. So the formula for the angle of departure phi d is equal to 180 degree minus phi. The formula for the angle of arrival is 180 degree plus phi. Then example, let us now draw the root locus of the control system having a open loop transfer function g of s into h of s equal to k divided by s into s plus 1 s plus phi. The first step we got to find out the roots. The roots of the characteristic equation is given as s equal to 0 or s equal to minus 1 and s equal to minus 5. So this characteristic equation does not have any 0, that is the numerator. Therefore the number of root locus branches is equal to the number of poles of the characteristic equation. Here we have 3 poles, therefore the number of branches is 3. So one root lies in between 0 and minus 1, and the second one between minus 1 and minus 5, and the third one lies between away from minus 5. The poles are located or shown in the above figure. The line segment between s equal to 0, s equal to minus 5, s equal to minus 5. Step 2, we will get the values of all the centroid and the angle of asymptotes by using the given formula. Centroid alpha equal to minus 2. The asymptote angle is theta equal to 60 degree, 180 degree and 300 degree for 3 branches. The first branch is having 60 degree, second branch 180 degree and third branch 300 degree. So the figure shows the asymptotes of all the 3 root locus. Then since 2 asymptotes have the angle 60 degree and 300 degree, 2 root locus branches intersect the imaginary axis. By using the Routh array method, special case, the root locus branches intersects the imaginary axis at j plus j root 5 and minus j root 5. So there will be one break away point on the real axis between s equal to minus 1 and s equal to 0. Then the breakaway point is calculated by s equal to minus 0.473. The root locus diagram for the given control system is shown in the following figure. The breakaway point is 0.473. Thank you.